Hi. Let's move on with in this video with the TCA cycle and how the two carbons are coming into the cycle. That's the input. And the enzyme that does that is citrate synthase. So it takes the two carbons from acetyl-CoA that we saw in the previous video how it is generated by pyruvate dehydrogenase and combines those two carbons with oxaloacetate, which is a 4-carbon unit, to give us citrate, which is 6-carbon units. And of course, coenzyme A is released as a product. Here we actually, this is the first time we see a carbon-carbon bond. How it is made? Well, in this case, if you go back to your organic, I believe organic 2, you will see that this is really a Claisen ester condensation. So the way it happens is this is one ester, okay, and you remove a proton, and now you made a carbanion again, okay. And the problem with the carbanion, as before, is that it has to be stabilized. So in this case, it can bounce on the ester bond back and forth. So you have the double bond here, and the carbonyl moves up, and so on and so forth. So you do have the carbanion stabilized because you have this extra way to push the electrons. And the carbanion, of course, will attack the other compound, in this case oxaloacetate, and that's it. It's a super simple mechanism. You got your joint, so to speak, condensation here. This is oxaloacetate. If you want to see it in more detail, this is oxaloacetate. This is acetyl-CoA. So the proton gets picked up, as I described in the previous slide, and you've made a carbanion, not shown here, but it's this double bond that can go back and forth and actually have the carbanion. So when the oxygen reforms the carbonyl group here, these electrons will go onto this carbon, that's the carbanion, which will attack oxaloacetate, the carbonyl of oxaloacetate, and you end up with this intermediate. Okay, it's already citrate, but it has a thioester bond from coenzyme A here. So all you have to do at this point is just hydrolyze the thioester, which also drives the reaction forward. That's a massive release of free energy. Okay, and you got your citrate, which is a 6-carbon unit, and now you have a normal, carboxyl group right there. So that's a tricarboxylic acid. It gives the name to the whole. It puts the T in the TCA cycle, so to speak. So we got citrate now, which has 6 carbons. Another special thing about this reaction is that it's stereospecific. So that's oxaloacetate, and depending on which side, which phase of oxaloacetate the acetyl-CoA is attacking from, you can get either the S form or the R form, and it is this one that is formed by the enzyme usually. All right, so this is what we have now, oxaloacetate plus the acetyl group that was on acetyl-CoA. During the condensation, by the way, the keto group of oxaloacetate, okay, becomes now, so the carbonyl carbon here, that's oxidation state, becomes reduced to hydroxycarbon. So the electrons of the carbanion, right, that was formed on this blue carbon here, on the methyl group of the acetyl group on acetyl-CoA, those electrons reduce during the condensation. They reduce the carbonyl carbon of oxaloacetate. So now we got our 6-carbon unit. Now, one of the substrates, I mean, does it happen? Well, one of these substrates is oxaloacetate, which is by far the lowest in abundance amongst all the intermediates in the TCA cycle. So based on the mass action, I mean, you want something that's favorable usually goes down the concentration gradient towards forming oxaloacetate, not consuming it into making something else. But the reaction proceeds because it is coupled to thioester hydrolysis, and that's it releases a lot of free energy, and you couple that to something super favorable, and then you can make it happen. Now, why do we need to do that? Do we really need to make citrate here? So what's the alternative? We have acetyl-CoA, and you can lose the CoA and decarboxylate, okay? And you're gonna have CO2 released here. And then you end up with something that's methylated. How do you oxidize this methyl group? That's the problem. The methyl group is fully reduced, right? That's a hydrocarbon state of oxidation. So in theory, it could happen, okay? You find something and you oxidize it down to a carboxyl group and then you lose it as CO2. In theory, what would you need for that to happen? And that is shown from our scheme. So you really want to write this reaction, hydroxycarbon to hydrocarbon. The methyl group is really on the hydrocarbon state here, and you want to reverse it. The only way to reverse it and make it favorable is to find something above here with an even more positive, okay, E value. And so that there are possibilities, but they're not very common in biological chemistry. It is for this reason that Krebs himself thought that it was impossible. So it turns out it's very difficult, but it is possible. It does happen in one particular bacterium, but it is difficult. Okay, and again, the reason is because you need something up there, okay, to get reduced for that blue reaction to run as an oxidation. So you do need a feeder compound here for the cycle, and that's oxaloacetate. A feeder meaning onto it you will attach the input carbon, which is acetyl-CoA. So that's the input, that's the feeder, and then you get started. And again, that's practically reversible. At least that's what you see in textbooks due to Thiester hydrolysis. But don't believe everything you read. A couple of years ago, a little over a year actually, it was reported that the cycle runs counterclockwise in some cases. Okay, how is that possible? All right, so in the clockwise version that you see here in the red arrows that we have, which is the canonical way. So we have oxaloacetate combining with acetyl-CoA to give you citrate, and goes clockwise. I mean, just have to rotate a little bit the cycle to put citrate synthase at 12 o'clock as opposed to 6 o'clock, but it's clockwise. And if it runs clockwise, as we discussed, you produce electrons and they find their way onto NADH and so on and so forth. So for the N plus, of course, you release carbon, okay, in the form of CO2. Whatever carbon comes in, it comes out as CO2. To run it counterclockwise, you have to provide electrons. Okay, so the electrons have to come from somewhere, and the CO2 is the input now, not the output. The CO2 will be the two CO2s will be the input, and the output will be acetyl-CoA. So it turns out that some organisms, some bacteria, they found a way to do it, okay? And the source of electrons, they are reduced nitrogen compounds, nitrites, and they're not as reduced as ammonia. So from ammonia, you get nitrites. We'll see this later, and then the nitrite becomes nitrate. So the more you remove electrons from nitrites, those electrons actually are used in this case to feed into the counterclockwise version of the TCA cycle. You do have to provide some ATP to reverse a couple of reactions, like succinate to make succinyl-CoA. We have it in reverse in the canonical TCA cycle. In fact, this is the only step where you actually get some ATP out from this by converting succinyl-CoA to succinate. And you also have to reverse with ATP the citrate synthase reaction, okay, if you want to, and that way you can make oxaloacetate. Now you do retain, this bacteria actually they still maintain citrate synthase, and the reason why they do it is so they can actually fix inorganic carbon into acetyl-CoA. Okay, so now acetyl-CoA becomes a product of citrate synthase, not a reactant. And you may ask, why do you need that? Well, you can use acetyl-CoA for biosynthesis, as we will see. You can use it to make lipids, but you can also, in some cases, use it to make even bigger things. So this is an ingenious way, because these bacteria, they have a source of electrons that other organisms don't, okay? And most organisms cannot pick up the electrons from ammonia or nitrite, but these guys can do it, and they can actually also use free carbon from the atmosphere, CO2, and use that to generate acetyl-CoA that way. It's a pretty cool thing. And again, you're not going to find this in any textbook, but the reaction can be reversed, the citrate synthase reaction. In fact, not just that reaction, but the entire direction of the TCA cycle can be reversed from clockwise as we draw it to counterclockwise. All right, so now we made citrate, and the next reaction is pretty simple. We don't change the carbon units. And in fact, we don't change any redox or anything like that. We change internally the redox state of the molecule, but from citrate, we make isocitrate. All we do is we move this hydroxy group from this position down one position. Okay. So it's a rearrangement, of course, it's an isomerization. And the way to move a hydroxy group is to take it out first. Okay, you dehydrate, and then you rehydrate. And depending on the rehydration, of course, you put the hydroxy group on the next carbon over, not where it used to be the hydroxy group, and you are done. You have now, if you dehydrate, okay, the hydroxy and another proton, we have seen this with glyceraldehyde 3-phosphate dehydration in the schemes that we're designing at the lower part of glycolysis. You will get a double bond, okay, and then you can rehydrate that double bond and put the hydroxy on the one carbon over. And the cis-aconitate here will be a key intermediate. All right, why bother with this? Well, look where the hydroxy group was on citrate. You cannot oxidize this anymore. Okay? It's a tertiary alcohol. But if you move it one position over, now it becomes a secondary alcohol, which you can oxidize it. And you can see it here from the hydroxycarbon, it can become a carbonyl carbon, a keto group. But you didn't have this option here. Okay? You can't have 5 bonds on this carbon. But here now you can have 4 normally. Okay. By forming the carbonyl, but here you would have had 5 bonds if you made the carbonyl, so it's not possible. But now the chemistry becomes possible. So the rationale, it favors oxidation of the compound if you just move the hydroxy. It makes it possible if you move the hydroxy up. Aconitase and a few other actually TCA cycle enzymes have been shown to have moonlighting roles. Now remember again, these are abundant enzymes found inside mitochondria in the matrix. What else is in there? Mitochondria have their own genome. There used to be a primordial, bacterium that could do oxidative phosphorylation that was engulfed by some primordial eukaryote, and we really have a symbiosis. Early on in evolution, the genome of the now mitochondria was pretty big, but most of the genes now finally they moved into the nucleus of the host. So the host pays for genome maintenance, and the mitochondria pays for oxidative phosphorylation. It's a win-win situation for both. The mitochondria doesn't have to worry too much about its genome. Most of it is in the nucleus of the host. However, some still remains. It encodes a few proteins of the electron transport chain. And the genome in mitochondria resembles more like bacterial genomes and not eukaryotic genomes with histones that pack and nucleosomes that pack the nuclear DNA. Mitochondrial DNA is still needs to be packed, but it's packed in a different way. And it turns out that more like the nucleoid in bacteria, and it turns out that in the absence of some mitochondrial DNA proteins that normally do this job, mitochondrial DNA remain stable because aconitase as a protein, nothing to do with its catalytic activity, is able to pack mitochondrial DNA. All right, so all we did here is we moved the hydroxy group one position, and that finishes the input now of the 2 carbons in the TCA cycle. And the next video, we'll see how the 2 carbons come out in the form of CO2.